So I realized that last time when I had the screen sharing set up here, that it was recording the my screen, not the screen. So hopefully that'll get fixed this time so that you can see the slides and not some weird presenter view that shows up on my screen. Okay, so before I get started in our lecture 2, do we have any questions so far about anything from lecture 1? Okay. So today's lecture is sort of one of those lectures that I like to give, even though, oh yes, question. Sure, we can go over that, but maybe not today, but next week I will be talking about it. And so you'll have some more background next week, probably about that as well. Yeah. But that, okay. So very briefly, it's just something to do with how computer scientists classify the types of problems, right? So like, I think the NP complete problems are the ones that are really, really hard. Okay, let me put it that way, right? Whereas NP hard are just hard. Sorry, I that's simplifying things a lot, but it's kind of like, you know, effectively what they refer to. We'll talk about it next week. Okay. All right. So today's lecture, the reason I'm giving this particular lecture is because the rest of the semester, we will be spending so much time on drawing quantum logic circuits and understanding them and figuring out like how to understand the quantum algorithms and going through the math of the linear algebra that you need, which we will introduce and all that. So don't worry, but you know, there will be a lot of math. There will be a lot of like, you know, as I said, talking about computer science, talking about NP hard problems and NP complete problems. And it can all tend to get a little abstract, I think, you know. And because we don't have a quantum computer kit that I can bring into the class, you know, it might even be hard to understand what is sometimes happening, you know, in the actual physical device. And so this little lecture that I give, and it might be more than one, maybe 1.5, hopefully it'll not be too long, is I want to sort of take you on a quick tour of quantum to show you how weird it is, okay? And the fact that, in fact, there are physical experiments that we do to confirm many of these things, this weirdness, okay? In fact, there's only one real weirdness, and we'll get to that. But from that come a lot of different other weirdness, okay? So that's why I'm doing this lecture, even though, as I said, for the rest of the semester, I'm probably never going to refer back to many of these things that I talk about today. But I might occasionally say, remember that? And hopefully you'll remember from this lecture, or you'll have the material to look at again. Okay, so what is this lecture about, now that I've hopefully piqued your interest? So we're going to talk about quantum, right? What is quantum? A brief history of quantum physics. Okay, physics is in brackets there. So we will discuss the strange behavior of light. We will see how people started to understand what is going on inside atoms. Then we'll introduce the central mystery of quantum, which Feynman called the central mystery. And that leads immediately to interference and wave-particle duality. Just brief raising of hands. People heard about wave-particle duality? How many people? Oh, okay, everyone. Nice, okay. And then we'll, again, as I said, probably again, we'll never refer back to wave mechanics or any of this stuff, but you should sort of understand that historically, this is how things happened in quantum physics. And then the modern viewpoint, which I'll briefly talk about. And then a couple of nice experiments, the Wheeler's delayed choice and Schrodinger cat. So I don't know if I'll get through all of that today, hopefully by next week. Okay. So this is just from last week. We talked about, not last week, sorry, last class. What is quantum? The physics of small objects. Oh, I see. I forgot to start the video. Okay. Is there anybody on the Zoom who can tell me if they're able to hear me?
Yeah, I can hear you.
Okay, very good. Yeah. Okay. Yeah, and the we talked about the fact that energy and momenta are going to be quantized. They're coming in lumps, little packets, and we're going to talk about how particles act like waves and waves can act like particles. So, and I already said that in the last class that in classical physics, this was at the end of the 19th century, so 1800, late 1800s, that by that point, it seemed like classical physics was at the peak of understanding of our universe. Like it seemed like the universe was completely well understood. We knew how to predict the motions of planets. We understood how to make engines and various other very, very interesting devices because of our understanding of thermodynamics and statistical physics. We understood how to send signals using electromagnetic waves with like radio waves and cable and telegraph, and all this thing was connecting the world up. So, and all of this came from the deterministic picture that classical physics had for the universe. Okay, except of course thermodynamics said, well, if you get to large numbers of particles, we're going to take a probabilistic approach. But in principle, everything was deterministic. If I told you all the positions and velocities of all these particles, we could predict exactly what is happening. Or if I told you all the amplitudes and phases of all the electromagnetic waves in the universe, I could predict exactly what would happen to that wave in later on in time. Okay. But then classical physics started to fail. Okay. And by 1930, in just 3 decades, scientists completely changed their viewpoint of what physics was. And in the nearly 100 years since then, we have tested this quantum physics to parts per billion, maybe even close to parts per trillion. I haven't found any contradictions. Okay. And the conclusion out of all that is actually nature is fundamentally probabilistic, even though it looks deterministic on large length scales, on macroscopic length scales, scales that you or I or any other living creature, most living creatures on this planet would find easy to understand. Everything looks deterministic. But when you get down to like subatomic, small length scales, everything is probabilistic. Okay. So what happened? All right. So the first story, the beginning of this story, is with something called black body radiation. So it sounds like a complicated word, but it's just the idea that anything that's hot emits radiation. Okay, and most objects which are at like say room temperature emit radiation, electromagnetic waves, light, which are in the tens of micron wavelength region. Okay, so that's like too long for our eyes to see, but can be picked up, for example, with infrared cameras. Okay, and back in once again, I should emphasize this is the work of many scientists over many decades who understood what black body radiation was. And what they found was that the spectrum, meaning the distribution of the energy from an object that's hot and that's emitting light, looks something like this. Okay. And so, okay, well, that's nice. All right. What does that tell us? Well, what you have to understand is that classical theory could not predict this spectrum at all. What they found that if they try to model what is going on in a black body and predict what its spectrum should look like. By the way, a sun is a black body. Okay? The sun is a black body and its wavelength is peaked around 500 nanometers, which is a green light. Okay. And that's because the sun is at a very high temperature. 6,000 Kelvin is the surface of the sun. Okay. And that's what this number is over here. You can see when you go to slightly lower temperature, it starts to move to the right, which is longer wavelengths. That's reddish wavelengths. You can see this started to go red. I wish I had chosen different colors. This should have been green and this should have been red, but okay. It's hopefully you understand what's going on there. Okay. The blue was meant to be cooler, but I should have said it's getting also longer wavelengths or reddish as it goes towards that to the right hand side. Anyway, coming back to my point, there became known in classical physics the problem of the ultraviolet catastrophe. Okay, catastrophe sounds really terrible. I mean, it's just a mathematical word. It was just like it was a divergence in their integrals that they decided to call the ultraviolet catastrophe. For theorists, it was like, what is going on? Our integrals are blowing up. Okay, all right. So this ultraviolet catastrophe was fixed by Max Planck in 1900. And to do this, he had to come up with a very radical idea, okay, which is completely did not make sense to people back then. Okay, he said a black body is a large number of little oscillators, but these little oscillators can't just emit light willy-nilly at any value that they like. They can only emit it in small discrete packets of energy. Okay. So he said the energy of each of these oscillators is some number, which is an integer, 0, 1, 2, etc., times some constant h, which got the name Planck's constant later on, times f, the frequency, which is 1 over the wavelength, proportional to 1 over the wavelength of the light. Okay. So that's the value of Planck's constant. You can see how small it is. And therefore, you can understand why people didn't observe it normally. It's on the order of 10 to the minus 34, right? In some, units. So it's very, very tiny. And that's why it's hard for people to have seen this in other classical experiments until then. Okay. But somehow it ends up mattering a great deal to this one problem, the black body radiation. Well, okay, people are like, oh, well, that's interesting. It's just one problem. I don't understand. Maybe we'll come up with a better classical theory that explains all this. We don't, there are still some, doubt that in fact this is happening at small length scales. But according to Planck, at least, the energy emitted by these radiators was quantized. Okay, and then the evidence started to mount for light being a particle. In 1900. I forget, Lebedev, I think, was the one who discovered that those little particles that the light could be composed of could exert momentum. In fact, this is an idea that people now think could be used to power solar-sailed spaceships that go in interstellar journeys. Okay? The radiation pressure from starlight or from like a giant laser that we fire off towards the other planet, we could use that to power some kind of spacecraft that can travel interstellar distances. But even more troubling were things like the photoelectric effect and the Compton effect. Okay. Again, look at how long it took for us to fully understand the photoelectric effect experimentally, to understand all the things that were going on. It started with Hertz in 1839, all the way to like Leonard in 1902, before we had all the experimental evidence about photoelectric effect. Okay. And then the Compton effect took another couple decades of work. So this, in some sense, it wasn't surprising. Newton in the 1600s or 1700s wrote a famous treatise on optics. Okay. And his theory of light was that light is in fact little particles of light, corpuscles that he called them. And these corpuscles go in straight lines. Makes sense. Objects cast shadows. That's because the light that's coming, like the particles of light are being blocked by an object. And so you get sharp shadows of those objects. And he was able to explain things like, many things. Anyway, so for example, one of the predictions of this theory, Newton's theory, is that if I take a screen, I cut a hole in it, and I look at what's happening behind the hole, well, taking into account some geometric factors, I should get a blob of light just where the hole is being cut, right? That was Newton's prediction. And if you had two holes, well, you get two blobs, right? That should be what you expect from this theory of light. But this was a 1700s theory. And Thomas Young, it took almost 100 years for Thomas Young to do the experiment. This long delay, I'm not going to why, but it's actually a tour de force experiment for that time, okay? Because it is very difficult to do this experiment. Even now, if I didn't give you a laser to do the experiment and you had to repeat this experiment, you would have to work quite hard. You have to think carefully about what light is. But okay, so he did the experiment. What did he find? He didn't find one blob or two blobs. He found many blobs, okay, with regions in between where there was no light and then regions where there was more light. This is the phenomenon known as interference, okay? So in our undergraduate modern physics labs, for example, we do this experiment with modern detectors and so on, we can get very clean looking fringes, interference fringes. We don't need to go that far. We can also just see it with our eyes. If I can dim the lights here. Oh, direction. Maybe it's those. So it is that. Can you? Yeah, thank you. All right. So in this experiment, you can see here, oops, back up a little. So on the furthest more, on the middle is the single slit, just like the Newton idea. This right-hand side is a double slit with red light, and the left-hand side is double slit with green light. And you can see what's going on. We're just zooming in. This experiment is easiest to do in a big classroom so that we can see. You can see the pattern, right? It's got these little blobs, many blobs from just two slits, okay? And with regions where there's no light. And this is the single slit pattern. It does look like a blob, just spreading out. Okay. So we have this experiment that was carried out by Young of the of this interference pattern, as it has been known. Okay, and this took another 50, 60 years for the development. Many famous names in this theories of wave theory of light. Young, Huygens, Fresnel, Fraunhofer, Poincaré, Poisson, etc., up to Maxwell. And the idea was, okay, when a wave, you can see these beautiful waves on, I thought I would illustrate with something that takes us to a place away from the cold, that, when waves of the ocean hit like an aperture, they create, as you can see, these ripple patterns, right? You can see that there, you can see that here, and even more beautiful here, right? I'm sorry, the screen, sort of the resolution isn't good enough, but on the actual, like on my screen, I can see like little ripples in each of these ponds. And so we see that when light hits these, waves hit these aperture, they spread out. That process of the waves spreading out is called diffraction. Okay, that's the consequence of the wave theory of light, or wave theory in general. And then you can see what happens when you have two slits. Okay, these two slits, and the waves are coming out. You see what happens, right? Where there are, you can see clearly regions where there are brighter and darker, brighter, darker, right? It shows up even more clearly here, where they are sort of patterning, interfering with each other. So that was explained then by this wave theory of light. Not going into details, but the waves come here, they hit this slits, they spread out, and when they spread out, they can create regions where there are maxima and minima. This is the wave theory prediction. And there are many, 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 many triumphs of this wave theory of light. So that by the time, finally culminating in Maxwell, who understood that light is just electromagnetic waves, right? He showed that light is just electromagnetic waves. And so from that, we could make lots of predictions. We used it for Hertz, for example, transmitted signals with radio waves and so on. So now, of course, in the 1900s, we have both these pictures now, right? The early 1900s. We just saw the evidence that it was a particle, but we have all this previous evidence that it behaves like a wave. Okay. Maybe you can turn the light on. It's a little too dark in here. Then we come to the atomic physics. Atomic physics, by 1897, J.J. Thomson had discovered electrons. And he proposed a model of the atom where electrons are just like in a little jelly, okay? Where the jelly is composed of positive charges to hold everything together. And the electrons are like little, cherries or plums, as he visualized it, in this jelly of positive charge. So the positive and negative charge cancel out, and together they stay held together in this distribution. Well, by 1911, Rutherford had shown that that wasn't the right way to think about the atom. In fact, the nucleus is very small compared to the atom. So for example, if the radius of the atom is 10 to the minus 10 meters, the radius of the nuclei is something like 10 to the minus 15 meters. And the nucleus is what he called the central region where all the positive charge is located. He did this by a very clever method of like just shooting things at the nuclei. Okay, so his idea was to take alpha particles. These are like our smoke detectors and so on. Like they use alpha particles to detect if there's any smoke in your house. So they're very sensitive. So these alpha particles come out and they were incident on this gold foil. And then occasionally you'd see most of the alpha particles went straight through, but then some of them were deflected by huge angles. And that wouldn't be true if this was just like a jelly through which the alpha particles went. They would just get slightly deviated, but they shouldn't be reflected back by huge amounts. That only happens when one positive charge directly sort of collides with another positive charge. Now suddenly you get big angles in the deflection. Okay. So that was his key evidence for the nuclear model of the atom. So if you look at the nuclear model of the atom, then people began to experiment and try to understand what's going on in the atom. And one of the things they discovered, which now you'll be able to do as well and see. So I'm handing out these glasses. Each of you can take a few. Back. Yes. Oh, it's stuck to that. You can keep these if you want. No. Yeah, that's good.
Brother, can you pass it over?
Oh, sorry. I thought you got some. No, sorry, I didn't mean to ignore it. Okay, so again, if somebody doesn't mind turning off the lights there. Oh, well, I'll wait till everybody puts on their glasses. Okay. Okay. Let's see. Is there a source of light you can look at? Flashlight or something. Maybe I need one of the lights back on. Let me put this one. Okay. Sorry, that's bright, but look at the lights in the room. What do you see? A rainbow? Everybody agree? Some kind of rainbow. It looks very smooth and continuous, I hope. I don't know actually with the LED lights how smooth they are. They may be more, are they shifted more towards one wavelength or one color in this room? I'm not sure actually. So you can see on each side of the of a bulb that there is there is a pattern, right? On each side, maybe on top and bottom as well. And you see that gradual change in the colors, right? Just as in a rainbow, as you said. Okay, yeah, I don't see particular shading towards one color or the other. Very good. Okay, now if you can turn off the light. Oh, I turned it on. Okay. Let me. Okay, good. Now, can everybody, are you able to see this light? At the back, you may have some difficulty. It's not, maybe not dark enough. Can everybody see that light? What do you see now? What is this? Okay, let me move it away. Did it light up yet? How does that look? What do you see now? Yeah, but is it continuous? What do you see instead? Slits, little sharp lines. Yes. Here's another one. The previous one was neon. And this is argon. Is the pattern the same? Very different, right? Another one. What's this one? Sodium. Sorry, I can't read right now with the lights off, but okay, so this is like a CSI for atoms, right? You look at the pattern of the lights and you can identify which species of atom you're looking at. Is everybody able to see this? One more. Oh. I had to jiggle it sometimes. Yeah, that one's cool. Hydrogen. I have to turn on this light here to read it. Oh, that's water vapor. Cool. Oh, that's nice. So yeah, so we saw neon, we saw, I want to put hydrogen in that if we have it. That one didn't work. Ah, there. Okay. That is helium. This should be cool too. Okay. So we saw a very different pattern from these than we saw from the room lights. And so now I'll ask you to turn your attention back to the screen. And you can turn on that light if you like. So, so this discrete wavelengths that are being emitted. So here's a hydrogen pattern, for example. They saw these clean, sharp lines, and they could identify the wavelengths of these lines and try to see what is happening. Okay, this is just a demo of the same thing on YouTube. I'll skip that. So they were very puzzled because they had seen the black body radiation. And they were like, okay, light is continuous in that situation, but it's not in this situation. That made them start to think again about the model that Planck came up with. But now we had these very sharp lines at very different wavelengths for each atom. How do we explain this? How do we understand what's going on in an atom? So Bohr, famous physicist, I'm sure you've all heard his name, proposed a model which was very much like the model for planets. Said, okay, we have this nucleus that Rutherford has seen, and we know the electrons. Okay, let's postulate that they can only go in certain discrete levels. Why? He had some vague arguments about why. Okay, not a really clear, but it was a brilliant idea. I mean, in some sense, to intuit that. But he said that they can only exist at certain distances. And he had a condition, a Bohr quantization condition for what that distance should be. And then he said discrete light emission comes from the hopping of the electrons between these orbits. So it's as if in his model, an electron, which is orbiting at say n equal to 2 quantum number, will hop to the n equal to 1 quantum number in like one jump. It doesn't exist in the places in between. Okay. Very weird, right? How can it do that? How can it jump like that? But that was a model. Okay. And what is wrong with the picture? Well, already there was something wrong with this picture. Even before you ignore the weirdness of it hopping between spaces without actually occupying any of the intermediate levels or spaces. This is already very weird for classical physics. But there's something even worse, which is that by Maxwell's theory, an electron, which is a charged particle, if it's going around in a circular orbit, it's undergoing acceleration. You all learned this in first your physics, right? If you have a particle going around another one, or anything that's going in a circular orbit, it's undergoing constant acceleration. Well, that is actually the criterion in Maxwell's equations to have radiation, meaning electromagnetic waves. So an electron that's undergoing circular motion must radiate electromagnetic waves. And of course, if it's going to radiate electromagnetic waves, it's going to radiate them continuously as it's going around this orbit, losing energy. And as it loses energy, it's going to spiral into the nucleus and boom, right? Complete implosion. So no atom can actually exist in this model with Maxwell's, if you take Maxwell's equations into account. So big problem, okay? Well, they didn't know what to do. Said, okay, we'll just assume for now, but obviously there's a big, confusion going on in quantum physics at this point, as it was slowly becoming evident that many of these things don't work. So it took de Broglie to propose, wait a minute, all this time we've been talking about electrons as though they are these little particles going around in like specified orbits and so on. But we already saw light was a wave. Light, which was a wave, is a particle. Why don't I go the other direction? I'm going to say that matter, electrons, which we have thought of as particles, that is how Thomson saw them first when he found that there are things called electrons. And J.J. Thomson discovered that, well, I'm going to go the other way and say, actually, electrons are also waves. These are de Broglie waves or matter waves, as he called them. And now he began an explanation. He said, this was his thesis, PhD thesis, okay? His explanation was lambda, which is the wavelength of the light, is related to the momentum of the electron. You don't need to know all this stuff for later. I'm just saying, this is how he thought about it. And what he said was, if there are electrons that are waves, now they can form standing wave patterns. Like, you all know standing waves, right? These are the kind of resonances that form in a pipe. They're the reason, like guitars and violins and all these different things operate at specific frequencies as you move your finger along them and so on. So he imagined that there would be these standing waves which form these beautiful patterns around the nucleus. And because the standing wave has a wavelength, which is given by this lambda, it can only fit it will only work if an integer number of these wavelengths fit inside an orbit. So an orbit is defined by the fact that an integer number of these wavelengths has to fit inside this orbit. And from that, he was able to reproduce many of the predictions of Bohr's model. Okay, so this is a beautiful idea. And so now we have come full circle that, okay, light behaves like waves, behaves like particles, and now matter, electrons, also behave like waves, at least in this Bohr model of the electron, of the atom. To make sense of it, we had to postulate that the electrons also behave as waves. Okay. And so we have arrived full circle. We know that energy and momenta come in lumps. That's because now when the electron moves between these patterns, it emits energy, and that energy is defined now by the energy difference between the two standing wave patterns. There's an energy difference because now you're occupying different space away from the nucleus, which is a positive charge. So you give up some potential energy as you move up and down through this landscape. And that kind of allowed them to explain a lot of things about, chemicals, chemical atomic shells, and the periodic table and nuclei. And then also eventually people like Linus Pauling started to postulate chemical bonding based on these ideas. Okay, so this is all wonderful, but you may ask yourself, okay, just like we had for light, an experiment that was a smoking gun for wave theory. What is that experiment? What is a smoking gun for wave theory of light for light? The double slit, right? And I've just told you matter or electrons is made up of waves. So what's the natural question? Yes?
They also have.
Excellent. Very good. Thank you. That is the central mystery. Okay. We are now going to look at the central mystery of quantum physics, the double slit experiment. And as in Feynman's words, this is the one experiment that's impossible to explain in any classical way. It has the heart of quantum mechanics. And it is, in reality, the only mystery, he says. Very powerful words, right? Okay, so I can't do the double slit experiment with electrons in the lab. It's a much more complicated experiment than the double slit with light. So I'm going to just show you a video. Okay.
What they want us to do isn't really the way it is, and that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says all the waves of information.
Sorry, is that loud enough?
I hope so. And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through it. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. These possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently. So it was aware it was being watched. It was here that physicists stepped forever into the strange netherworld of quantum events. What is magic? Bubbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply observing.
Okay, so I want to say that we don't talk in this language anymore of the collapse of the wave function, but we'll sometimes fall into it. But we have a better way of describing all this now than we did back in the 1930s or when this experiment came out. But this is sorry. Okay, so here's actually the experiment from a paper. I should have put the reference so we can go look at it. Beautiful paper. I think it was voted the most beautiful experiment of 1970s, I think, when this was done. And yeah, I mean, it is exactly as described in that video. So they shot electrons through a double slit, and when they were measuring each of the electrons, as you can see, it forms a single dot, right? It seems like it's randomly just appearing on the screen. But over time, as you build up more and more electrons, after an hour or 2 hours, or I think it might have been days, they see the double slit pattern. So each individual electron looks like it's just a particle when it hits the screen. But before that, if you want to think about it, it's looking like it passes through both the slits at the same time. And of course, they did all the control experiments and etc. This is all well established at this point. Okay. Okay, done. So it's funny. After I had found this first video, my kids and I were watching Teen Titans. Okay. My kids love Teen Titans. And what do I find but this amazing episode with this amazing song and animation? It was too good for me to resist. I had to show everyone. So everyone who knows me will know that I know that I put this video up for. And, let's,
so you pour that sand diabolical. So what do you get? To this conversation, when you go and take a whole lot of deep electrons and one person say, shoot the meat.
I really love this. Oh, sorry. I was actually looking at this board and I was like, oh my God, those are like the Trotter formulas for like a time evolution of a Hamiltonian. Like, my goodness, who did they have advising them? I want to be an advisor for Teen Titans now. Okay. All right. So, okay. So maybe as a extra credit assignment, we'll have you all create your own rap video for the double slit. Okay. You can work in teams, no problem. The best one gets a prize. Okay. All right. Back to the serious one. So if matter, of course, is waves, then atoms make sense, right? We just saw the de Broglie-Bohr sort of idea. And we also see that matter had particle properties. That's how Thomson, Rutherford, all those people discovered what the atom was made of. And again, we are back to the same conclusion, right? Matter behaves like waves or particles, depending on what observation measurement that we make on it. Okay. And Bohr was just baffled, right? He was just like, if anybody claims that they've understood quantum physics, then you know that they're lying because it just makes no sense. Okay, so for the rest of this course, this is what we're going to assume, right? This is how the only thing I can tell you is, yes, weird as it is, this is how it actually is. There's no escape. This is reality, man. Okay, so you just have to like get with this program that this is how the universe behaves, and we have to just accept it. Okay. And then of course we start to take advantage of it and so on later on. But okay, one question you can certainly have is, what is this wave? You know, is this a wave of potentials like that cartoon character claimed? What exactly is this wave that they're talking about? So Schrodinger, he said that the position or any other property of the particle, whether it's an electron, atom, etc., is governed by this matter de Broglie wave. And he postulated a wave function, psi, turns out to be a complex number, not just one number, but two numbers at every point in space and time. Okay, so complex number. And that complex number obeys some equation. You don't need to know what the equation is, how it works, etc. It's just it's a wave equation. Physicists are very, very comfortable with equations, differential equations, wave equations. And this was the wave equation he postulated and then proved that with this equation, he could explain all the properties of, say, hydrogen atom. Okay, that was a real magnum opus for physics that he could predict from this equation. And then from then on, things just develop exponentially. But we still had a problem of interpreting what this wave function, psi, so this symbol, by the way, is capital psi. Okay, you'll see it again later on. And this psi, it wasn't until Max Born, who said, what I think is really happening is that the modulus squared of this wave function, again, just some mathematical operation, is proportional to the probability of finding the particle, okay, at that point. So now this is what I meant by we had to adopt this probabilistic approach, just like when you saw with the electrons. At any given time, we couldn't predict where the electron would end up, okay? It could be anywhere on that screen, right? But we can say it has a higher probability to be in one of the bands, the interference bands, and a lower probability to be in one of those darker bands, okay? That's all we can say about the motion of the electron through those double slits. So it's a completely new way of thinking about what particles are doing, because we can no longer claim that we know what they will do exactly. We can only assign probabilities to different events. And as we move through this course, I mean, something that, I don't know how many of you have had a statistics course or probability course. Some of you? Okay. We'll talk about probability, so it's not going to be completely, but this is something that as people, we move through life and we have to deal with probabilities all the time, right? In some sense, you're just your brain is just this, probability sort of calculation machine, right? When you make decisions in your daily life, should I walk across the street? What's the probability I'm going to get killed by a car, right? So this is kind of your brain is evaluating these probabilities at every instant of time and making a decision. Okay, it's safe, I can walk through, like so on and so forth. What's the probability a comet is going to come and crash into me right at this very second, right? I mean, these are all, things that we consider, right? At some point, at some level. Okay, so that is what is going on. And that's what the quantum wave function or the quantum state of the particle that quantum mechanics gives us is calculating, okay? And we'll come back again to this. And the modern formulation of this, so by the way, Heisenberg, at the same time as Schrodinger, Heisenberg came up with what is called the matrix formulation of quantum physics. And Dirac showed that, Dirac and Pauli, I think, maybe also, Schrodinger and Heisenberg pictures were equivalent, okay? They are the same, especially when you supplement it with the Born rule, okay? And our current formulation of the non-relativistic quantum physics is reduced to just 4 axioms, okay? So for 4 postulates of quantum mechanics, they're the Dirac-von-Neumann axioms or postulates, and we'll introduce them when we come back to qubits and quantum states and so on. And all of the progress has just followed from these 4 postulates of quantum physics. Okay, so that's our summary. Let me see. Oh, I still have some time. Cool. All right, and the summary of where we are with our past knowledge of quantum physics is that particles can act like waves. They can be in superposition, multiple places, multiple states at once, and then there can be interference between those possibilities. Okay. And of course, waves act like particles. The standard example is the photoelectric effect, which of course, in case you don't know, we use that all the time in our cameras and so on, because the light that comes into our cameras is collected and put onto like a little chip. And that chip is basically using the photoelectric effect to detect that there was a photon, a particle of light there in that location. Yeah, I'm going to stop for a second. Any questions? I've gone through quite a lot of material. So, yes.
They really, I know they did the double slit when like they observed the electron.
Yeah.
And then it like showed how. I'm sorry, I thought about it.
No. Yeah, go ahead. I'm going to talk some more about the double slit. So you're welcome to ask me anything.
Yeah, I always been confused if like observing it really did like literally make it cause to be like in two outcomes, or
Yeah.
just like each atom, each electron individually behaved as expected, but did it, you know what I mean?
Yeah, and I think this is getting into the realm of like ontology, right?
Yeah, I hate when they like say like the electrons decide to do something.
Yeah, no, that's like us, anthropomorphizing the electron, like, oh yeah. But I mean, sometimes that helps us, right? I mean, when we think about probabilities, for example, that's one way we think about like what might be happening. Oh, the coin decided to flip in a certain way or something like that. And we can, and as human beings, I think we deal with counterfactuals all the time. What if this hadn't happened? Then what would we have done? Right? That's the way we think. That's causal reasoning. Okay, because we are used to dealing with cause and effect in daily life, and we want to assign causes and effects to each other. Okay, and I think that's the real problem with physics, with quantum physics, is that cause and effect become very hard to disentangle from each other. Okay, but I'll come back to the double slit and that question of yours, which is, we can actually make that contradiction or that puzzle more sharp. Okay, so but to give you a broad story, the electron is getting entangled with the slits. Okay, and that entanglement, when you don't observe it, depending on what you do with that information, that is the entanglement, you either will observe an interference pattern or will not observe an interference. The other way to say this is the original explanation that people like Einstein and Bohr came up with is, as the electron moves through the slit, okay, if the slit is narrow enough that it causes a change in the motion of the electron, so that we know, oh, the slit moved up, this must be they had this beautiful idea, like, maybe you can have a moving slit that will register if an electron goes through it or not. Well, the movement of the slit imparts a momentum, a recoil momentum to the electron, and that changes the motion of the electron sufficiently to smear out the interference pattern. So this is another way of thinking about it, which is similar to the entanglement idea that I will discuss when we get to entanglement. Yes, you had a question there.
I was just going to ask you, it's a related to entanglement.
Yeah, very good. All right, we'll introduce. Yeah, another question.
That's like I thought that like observing it applied some momentum.
Yeah. So entanglement, decoherence, all of this in the modern view of quantum mechanics, entanglement, decoherence, all these things are very closely related to each other. Okay. And so when we talk about that, we'll introduce this again. Yes.
Another quick question. With respect to the given the recent discovery for the Nobel Prize winner.
Yeah.
After you measure it, it travels faster than light to let the other particles know that. That's what I've read, but
No, that's not true.
couldn't make.
No, it's not true because okay, we'll come to those experiments, the Bell's inequality experiments and so on, but that is no faster than light travel. Okay, the information that you need to tell whether there was any correlations or whatever has to still be communicated before you can tell anything, and that information is communicated through optical fiber, radio, whatever. Is going to be limited by the speed of light. So, yeah. Okay, so let's talk about this, the single photon interference. And the reason I talk about photons now instead of electrons is just because they're so much easier to do the experiments with. Okay, as we saw already, right? The Young's double slit was first discovered with light. Okay, even though they didn't have great light sources, they were able to do it because light is has such obvious wave-like properties. Okay. So nowadays, just like we had the single electron gun in that experiment that was done in the 1970s, 80s, nowadays we have access to single photon sources. Okay, this is something that we didn't have access to, say, 50, 60 years ago, but has now become very commonplace. Well, commonplace in a research lab and also in other settings in companies and so on nowadays. So a single photon source is exactly what it means. It means that instead of emitting, like a laser emits like billions of photons, like in that, that video I showed you, you could see very bright, double slit interference patterns. Even the light that's coming from, one of these lamps is immense in terms of the number of photons that are present in the light beam, because we know that the Planck's constant is so small, right? H, the Planck's constant is so small. So that means that if I have any intense source of light, right, even a 60-watt bulb or whatever, and I could be like miles from it, and I'll still be able to see it. There's few photons coming out of that, right? So when I'm closer like this and I'm very near this photon source, there's like billions of photons incident on my eyes. Okay, so normally so many photons, it looks like just classical, like it travels in straight lines. It looks like there's sharp shadows and so on, and there's no interference going on, and we have to work a little harder to see the interference pattern. A single photon source, on the other hand, is one, just like the single electron gun. Now I get single little packets of light coming out. And of course, the ideal situation we would like is they come out like a gun, right? They come out exactly I'd say once every 1 second or once every 10 seconds, whatever rate that we want. We don't quite have that. It's a little bit more random than that, but at least when they come out as single photons. So we know that there's only one photon in that packet. So it's an extremely tiny amount of energy that's coming out. And so we need detectors, which are called single photon detectors, that can pick up that one photon came through as well. So that's also been a huge development in our field, which has been enabled by the photoelectric effect, another quantum phenomena inward. Okay, so if I take a single photon source, remember only one photon can come through. The reason I'm doing this experiment this way instead of using a Young's double slit is it makes the distinction between quantum states much more visible, and we can assign bits, digital information, to this system very easily here. So I take a single photon, I send it into a beam splitter, which basically has a 50% chance the photon will go straight through, or 50% chance it will be reflected up into this arm. Okay, so in this way we have what is called a two-mode qubit, basically a double mode qubit, because one mode is going to the right, one mode is going to the top, and we can say that if the photon is in this mode, it's say 0. If the photon is in that mode, it's a 1. Okay, and of course the detector will click when I get a photon in one arm or the other. Okay, so this is the advantage we have now with modern instruments. And actually now, if you go to in our modern physics lab, we actually have this kind of equipment. We have the ability to send single photons and like observe these kind of clicks from like these single photons in the detectors there. So now we create what is called an interferometer. This is just a more complicated version of Young's double slit. Okay, so the idea here is the single photon has one beam splitter, right? So it can take one of either the top path or the bottom path, right? And then it recombines on this beam splitter. Again, at the end, it can either go to the top or to the bottom, to the right. Okay. And we can arrange matters by interference, right? We can arrange the path lengths of these interferometers to say cancel out entirely the possibility that it appears in the state over here, say 0 or 1. So this will deterministically almost always produce a 1 or a 0, because we can arrange the interference here in the interferometer by moving the path lengths and adjusting the phase of the wave function such that you get complete constructive interference on this side or destructive interference on this side and complete constructive interference on the top side, right? Because we know that waves can have constructive and destructive interference. We can arrange the situation in that way. Okay. So let's think about the system. So we've arranged it so that light always ends up, say, in the top detector. You always get a click here. You never get a click here in the ideal conditions. Okay. Now what will happen if I block one of the arms? Yes. Yeah. So now what will I get? Light will sometimes end up here, sometimes end up there, right? Because we don't know, with 50% chance that it might go one way or the other. Okay. It's kind of weird when you think about it. Like before I put something in that blocks light, I had no light going to this detector. Right? Before, like I didn't have anything in the path and no light was appearing here. I put something in this path and I make light go here, right? It's kind of, if I was just sitting over here, I'd be like, oh, that block, man, that's like adding photons or something into the path for me to look at. Okay, so the point is that by choosing which detector I'm looking at, I basically am able to get interference or not get interference, right? And by putting these blocks and so on, I can decide when light will go to both detectors or just to one or the other and so on. But now imagine, oops, sorry, that should have come up second. But now imagine that, ignore this bottom for a second. Imagine that I can move this last beam splitter in and out. Okay. So first imagine that there's nothing, there's no beam splitter. Okay, over here. Then if light takes path 1, it'll always end up in detector 1, right? Because there's no beam splitter here. Okay. If light takes path 2, it'll always end up in detector 2, 0 or 1. So the presence of a 0 or 1 tells us which path the light took. This should start to remind you of the electron double slit experiment. The presence of the beam splitter and the click, or sorry, absence of the beam splitter, and then a click in detector 1 tells me path 1 or path 1 for detector 1, or click in detector 2 tells me the path that it took was detector 2. But when I slide the beam splitter in, okay, now it'll deterministically, I can like, I should have, I should have said this, but yeah, if instead of arranging it so that things are exactly, going to 1 or 0, I can go between those, right? So I can continuously tune the interferometer to have either all the photons in 2 or 1 or anyone in between as well. So like I can have photons sometimes in 2, sometimes in 1, or all the way in 1 and then back. So it'll be looking like an interference pattern again as I tune the length of the interferometer. Or in this case, just by tilting this last beam splitter, I can do the same thing. So mentally, just maybe I should have brought a pen, but I'll just sketch it. So if I were to, I have a variable phi, which is the phase of the interferometer, and I observe the counts, the intensity, the counts in detector 1 or 2. Then I get something like that as I tune the fringe, the interference of the interferometer. So it doesn't go below 0, of course. And the other detector will obviously have the opposite pattern. Okay. And that is just by tuning this interference of this interferometer. But now, as I said, by deciding when I put the beam splitter in or out, I can decide whether there's an interference pattern or whether I know which way the photon came into the interferometer. The key is I can decide, if I create this experiment because of the arms of the interferometer, I can put this final stage very, very, very far away. So far away that the decision of when to put that beam splitter in is taken after the light would have hit the first beam splitter. So that we don't know that. So what I'm trying to say is the fact that there is an interference pattern, okay, can be decided well after the photon has already crossed the first beam splitter. So now we arrive at this sort of question: when did the photon know that it had to go along path 1 or path 2. Because we know that if we don't have the beam splitter and we get a click in detector 2, it must have come along path 2. If we don't have the beam splitter and we get a click in detector 1, it must have come along path 1. But the question of when I put the beam splitter in or out, I take well after the photon has already hit the first beam splitter. Yes.
How far away does the beam splitter have to be?
Yeah. In this experiment that they did, this is a real experiment, Science 2007. They put that second, I mean, ignore all this is the actual experiment, not the way I sketched it for you, but this is the real experiment. Okay. And this path, so here's path 1, here's path 2, just like our interferometer, and here are the detectors 1 and 2. Okay. And ignoring all the rest of this in between, they were able to decide whether to include the interferometer, include the last beam splitter. This is like 48 meters. So, light is traveling like 30 nanoseconds, right? I mean, it takes 30 nanoseconds for light. Sorry, I'm getting this wrong. In 1 nanosecond, it travels 30 centimeters, 1 foot. Okay. So 48 meters, you can convert that, how many nanoseconds that is. And you see that if you can do it fast enough, which you are able to do with modern electronic communications and so on, they were doing it with random numbers so that nobody could tell when the beam splitter is moved in and out. So the question was, would you see interference if you randomly decide to put the beam splitter in or randomly decide to take it out, and you do this well after the photon has already hit the beam splitter? So now it seems like, if you think about like the retrocausality that you were talking about, like, does the photon already know which path to go on? Now it's even worse than that, right? Because I'm sliding the beam splitter in. So that would seem to imply that the photon had to go along both paths to cause the interference. But I make that decision well after the photon has already gone down the beam splitter. And if I remove the beam splitter, then it's only in path 1 or only in path 2. So that which way information is only available well after the photon has already gone through the beam splitter. So this is the weirdness again, right? This is called Wheeler's delayed choice experiment with classical erasure. Classical because the choice of whether I move the beam splitter in or out is taken by a classical signal. It's just some noise that triggers some classical decision, okay, in the process. Does this experiment make sense? Like what they were doing and why it's kind of weird? I guess it's only weird if you think that the photon somehow had information about the interferometer that was telling it what to do, basically. Like the fact that the photon could decide whether to be in both paths or be along one path or the other is decided when it enters the first beam splitter by its knowledge. There's something in the setup, there's something about nature that tells the photon, okay, now I want you to behave like a wave, or now I want you to behave like a particle. And if this is this is called a hidden variable theory, basically. There's some hidden variable that tells the electron, which we can't observe, but which, or photon in this case, which path to go on, or to behave like a wave when it doesn't, when that setting is at the right variable setting. So there might be a variable which says, okay, behave like a particle. Oh, behave like a wave. And this variable is somehow baked into the system. And the decision of when it's going to behave like a particle or a wave then would have to somehow propagate back to the photon even before it entered into the system, right? Because in this case, I'm moving that beam splitter in and out well after the photon has already entered into the system. So there would have to be some propagation backwards in time to tell it, oh, do this now. Okay. Oh, wait a minute. We changed our mind. Oh, no, don't do that. Do this instead. Okay. Again, this is only a mystery if you think that, if you don't know about entanglement. So we will talk about entanglement. All right. I'm out of time, so I'm just going to summarize. There's one other Wheeler's experiment. I'll just briefly mention it. It's called Wheeler's delayed choice with quantum erasure. So far, remember, I just told you this was Wheeler's delay choice with classical erasure. That's because erasure means, erasing which way the photon went. We don't know which way the photon went, so we get interference. But if we know which way the photon went, we don't get interference. So that erasing of the information, the which way information, happens through a classical signal. But we can also do it with quantum signals, meaning we can take quantum objects, and those quantum objects will tell us which way the photon went. Okay. And now we start to get into really entanglement between particles. Okay, I'll talk about that briefly next class. But for today's lesson or today's lecture, we are just summarizing the weirdness that is at the heart of quantum science, which is the superposition and interference principles. And that leads to a lot of counterintuitive effects. If you have any more questions, I'm here, we can talk some more. Oh, yes, please, yeah, if you can hang on to them, but if you have extras, please give them back. Yeah.
It's kind of tangential.
No, that's okay. Tangential is what we're about.
What are the logistics of making a single photon?
Very good. Good question. Let me just end this.